Okay, so before we get to our toy car lab today, we're first going to take some notes on graphing motion, and then we're going to at least start talking about the lab you'll be doing. Again, you should have already picked that paper up from the front of the room, and we'll talk about it again later on. So for now, just set it to the side and have out your notebook so that you can take some notes on graphing motion, which is part of Playlist 2. Again, as a reminder, Playlist 2 is due by the 12th, which is next week. Today is the 7th. The 12th is next Tuesday. That is the due date for all of those task options and the checkpoint for Playlist 2. All right, so we're going to start with position versus time graphs. We talked about one representation of motion in our previous notes, and that was a dot diagram or motion map. But I made mention of other types of representations of motion, including position time graphs. So we're going to talk about those today. A position time graph will plot your position on your y-axis and your time on your x-axis. Your positions are always shown with respect to a stationary reference point, that is your frame of reference, and the x-axis is your reference point because that is the position of 0. And so whatever your reference point is, you will call that position 0, and then you will measure the motion of objects or their change in position with respect to that reference point. And so if you look up here, you can see what a position time graph with no data on it would look like, but you have your position on your y-axis. Position, the variable is x. It is measured in meters typically. And then on my y-axis, I have time. My variable is t, and we're going to measure in seconds typically. Anything that is up here in the above the reference point is going to be a positive position. So if I have a point or some data that starts up here, that means that my object, whatever it may be that I'm measuring, has started ahead of the reference point or on the positive side of my frame of reference. Again, depending on what that intercept is, I can look at the starting position of the object. Any positions down here are going to be negative, meaning that I am now behind my reference point, my 0 point on my graph, and I would represent those with negative numbers. And so you should be able to interpret a position time graph and be able to look at where you're at with respect to the reference point simply by looking at whether you are in the positive region of the graph or the negative region of the graph. And of course, the reference point itself is right here along the x-axis where my position is 0. What do you think the y-intercept means on a graph like this? What does this value here mean versus this value here? My starting position. I kind of already said that a minute ago. But it's where I started. So if I look at this graph, I have a starting position that is in front of the reference point. There's no numbers on my axis here, so I don't know what it is, but I know it's positive. Whereas this one represents an object that has started at the reference point. Okay, but the y-intercept tells us our initial position, x at time of 0, okay, which is what x sub 0 or x naught means, is your x position at time 0. All right, so let's take a look at another graph. It says, what can you tell me about this object's motion? What happens to its position after 1 second? Guys, what is this object doing?
It's moving at a constant speed.
I have moving at a constant speed and I have not moving. One of them is right. It's not moving. Okay, that's okay. It's new. You're good. Okay, it's not moving. This object is at a position of 6 meters with respect to whatever the reference point is. It's 6 meters ahead of it. Okay, but it's at 6 meters the entire time. And if you're at a position of 6 meters the entire time, you're not going anywhere because you're staying in the same place. So if you see an XT graph with a horizontal line, that will always be the case. A horizontal line on an XT graph is going to represent an object that is not moving. That object will be at rest, either for the whole graph like this, or maybe just a portion of your graph if you're looking at something where you have different segments and you have motion and then maybe it stops and then it moves again. Okay, but again, if you look at this, a horizontal line on your XT graph is going to tell you you're not moving. So If you want to jot that down in another way, here's how you would graph something that's at rest. No motion, at rest. On your XT graph, you're going to see a horizontal line, meaning that your slope is 0. And it could be at any y-intercept. It really just depends on where that object is. If I call the reference point, where I'm currently sitting, then my stapler, if I call that the positive direction, might be at a position of 1 meter. Okay, whereas if I look, farther at like their table, it might be 2 meters. But it doesn't matter. Neither one of them is moving. This would be 1 meter the entire time. That would be 2 meters the entire time. So any y-intercept, and then my board behind me might be at 0.3 meters the entire time. Okay, so any y-intercept, but if you have a horizontal line, you have something at motion, at rest, not in motion. Okay, so this would also be an example of something at rest. How would I show constant forward motion? Well, if I want to show that something is moving at a constant speed, okay, that means it needs to move, let's say, 2 meters each second, then I need to see a line with a constant slope. That each second that passes is 2, and then 2, and then 2, and then 2. And so you're going to see a straight line. Okay, forward motion specifically means that I need to see a positive slope on my line, because that means I am moving in the forward direction away from 0 here, or toward more positive numbers, if you will. Okay, and it can't be a 0 slope, so it's a non-zero positive slope. Because of course, if the slope is 0, then I'm not moving. Okay, so non-zero positive slope is going to show me that I have constant forward motion. But again, it could be at any other y-intercept as well. It could be down here. This is also constant forward motion. Okay, so it doesn't matter, again, where we start in terms of whether we're moving forward or not, or whether we're moving at a constant speed. Both of these are examples of that. Now, these don't have the same speed, okay, because they have different slopes. Okay, and so the slope is going to tell us what the velocity of the object is. Okay, which of these is faster? What do you think? The one on top or the one on bottom? Bottom, because it has a greater slope. Okay, again, if slope is rise over run, or change in my y-axis, which means change in position over time, this one is going a farther, or having a greater change in position each second. That's why it's steeper. Okay, the steeper the line, and you can add that to your notes, the steeper that line, the faster that object is moving. Okay, and of course, as you get more and more horizontal, you're closer and closer to stopping. And then, of course, when you are completely horizontal, you are stopped. Constant backward motion. Okay, the only difference here is that now we're going to have a negative slope to our graph. Constant forward was a positive slope, but again, constant backward motion is any negative non-zero slope, but again, it could also be down here. Okay, this is also something that is moving constantly backward. Okay, and they don't have the same velocity, and I know that because my slopes are different. We just talked about that. So again, constant backward motion, you're going to have a negative slope. It needs to be a straight line. Okay, non-zero slope. Looking at these two lines, which object begins behind the reference point? That line on top or the line on bottom? Which one begins behind the reference point? The bottom one. This one starts at some positive position. I don't know if there's no numbers. Let's call it 3. This one starts at -1, for example. There's no numbers, but this would be behind the reference point. Again, the reference point being my x-axis or position of 0. So if you want to add any extra notes on these little questions I'm throwing in there, you can. All right, so looking at these graphs, now we know how to show forward motion, backward motion, and no motion. Now we have a graph that has all 3 of them. You can interpret different things by looking at a position time graph like the one on my screen. It says, what is the distance traveled by the object in the graph, and what is the displacement of the object in the graph? And these are 2 different terms with 2 different answers. Again, when you did your definitions tasks, you should have looked at each of them. But the main difference being that your distance is going to be a scalar quantity, and the direction that you're traveling doesn't matter. So if I was to walk from here, let's call this my reference point. Okay, and let's say that anything that I go this way is in the negative direction and this is positive, right? Like a number line. Okay, and so if I start here, let's say that I walk -5. Okay, my distance is, I'm 5 meters, if that was meters, we're going to pretend. I'm 5 meters from where I started. My displacement is not just 5, but specifically 5 meters to the left, okay, of where I started. I need a direction. I can call it -5. Okay, so I walked 5. Let's walk back 2 this way. Okay, so if I walked 5 in the negative direction and then 2 in the positive direction, my distance is the total, basically, steps that I took. 7. My displacement, what is my displacement? How far am I from where I started?
3 to the left.
-3. 3 to the left, or -3. Okay, and so the displacement's going to take into account the direction as well. Okay, so if you need to jot any extra notes down about those terms, because I know you've seen them before, but you can add anything else. But let's talk about how to read them on this graph. Okay, so taking a look at this graph, what is the distance traveled? What is the displacement? Whatever this object is starts at the reference point. And then it goes, in the first 10 seconds, it travels 60 meters in the positive direction. Okay, so I've got 60 meters forward. Okay, then what does it do? It stops for 5 seconds. And then after that, it starts to go backward. And it goes backward from 60 to -40. How far backward did it go? 100, right? 100 meters backwards. If you want, you could break that into 2 parts and say, okay, it goes from 60 to 0. Okay, 60 to 0, of course, would be back where it started. And then it goes from 0 to -40, which would be 40 more. You could do that if you want, but this together, of course, is -100. Okay, and then it stops. So I need to answer these 2 questions. What is the distance that it traveled? Well, if I'm looking at distance, I don't care what direction I went. I don't care if it's forward or backward. All I care about is how far I traveled. I traveled 60, and then 60, and then 40. So how far did I travel in terms of distance? 160. Okay, that would be my distance, 160 meters. My displacement, on the other hand, it matters that I went forward and then backward again. My displacement is a vector quantity. The direction matters. Now I have to take these into account. What is my displacement? What is my change in position? -40. I can see it mathematically, because those cancel, and then you got that left. But you can also look at the graph. Okay, I started at 0, I ended at -40, my change in position is -40. Okay, displacement's a lot easier to see on a graph than the distance. The distance, you have to take everything and add it all together. Displacement, look at the starting point, look at the end point, find the difference, that's your displacement. Okay, any questions about distance versus displacement? All right. Is it possible for displacement to be greater than distance? I see one head shaking no, and a bunch of silence. It is not. Displacement, by definition, is always how far you are from where you started. It's your change in position. It's always a straight line from your starting point to your end point, wherever it may be. And there's the shortest distance between 2 points is a straight line, so there's no way for it to be shorter. It could be the same, because again, if all I do is this, I start here and I go like this, in one direction, and I don't turn, my distance and displacement have the same magnitude. Okay, they're both 5 or whatever. Okay, but they can be equal, but your displacement cannot be greater than your distance. Okay, if you want to make a note of that, you're welcome to add that to your notes. All right, so we talked about position time graphs. Let's go ahead now and talk about the second type of motion graph that you need to know, which is a velocity time graph. Again, yesterday in your notes, we wrote down that there were 3 different types, and I said we're going to hold off on acceleration for now, so we're going to focus on the first 2. A velocity time graph plots velocity on the y-axis and time on the x-axis. The x-axis represents 0 velocity when the object is at rest. And so if you take a look at this graph, anything in this region up here now means that I am moving. Okay, I'm moving forward specifically, but if you have data points up here, you are in motion. because all of these values are greater than 0. Okay, so my velocity could be 1 or 2 or 3 or 4 or whatever. If you're in this region of the graph, you are moving forward. If you are in this region of the graph, you are moving backwards because now my velocity is -1 or -2 or -7 or whatever it is. And of course, if you have something that is on this line or if it touches this line for a brief moment, then your object has either is at rest or maybe stopped momentarily. Okay, but if you're on this line, you are at rest. Either you're staying at rest if you have a long segment there, or you are momentarily stopping before doing something else if you just touch the line. Okay, so the x-axis represents 0 velocity. Be very careful whenever you read the graphs, because obviously if you look at a graph like this and interpret it as if it was a position time graph, you're about to get a bunch of things wrong. Make sure you read the y-axis so you know what type of graph you're looking at. Note, you cannot determine starting position from a VT graph. Okay, so if I have a line on here, just any line, I have no idea where my starting position is. I don't know where my reference point is. A velocity time graph does not show me that. It simply shows me, am I moving or not initially? Okay, I could be initially at rest, or I could be initially moving or something. Okay, but you cannot determine starting position from a VT graph. You have to have a position time graph to know where your reference point is or where you are with respect to it. Or it's told to you in the question. All right. So let's talk about how we can graph different things on a VT graph. How would we show something at rest on a VT graph? Well, I just told you on the previous slide. That is what it would look like if it's at rest. So it is a horizontal line, like last time, except this horizontal line has to be on the x-axis because that's the only place on this graph where the velocity is 0. So this object is sitting at rest. It is on the x-axis. My velocity value there is 0. This is not moving the entire time. Okay, so that's how you would say something or show something not moving. If you want to show something that is moving with a constant forward velocity, it would look like this. Okay, if I want my velocity to be constant, this one is constantly, 4, whatever that y-intercept is. I don't have any numbers. Okay, so maybe this is a constant velocity of 4 meters per second or 2 or whatever the number happens to be if you were to number it. Okay, but I know it's forward because it's +2 or it's +4 or it's positive whatever value this is. Okay, so the slope is still 0 because if I had a different slope, then that means my velocity is changing, which means it's not constant. Okay, because if I had a slope, I would have a changing velocity value. We don't have that yet. Okay, so constant forward velocity looks like this. The line needs to be in the positive region of the graph, meaning it needs to be above the x-axis. It doesn't have to specifically be there. It could be right here. Okay, it doesn't matter as long as it's in the positive region of the graph. Constant backward velocity, same thing. You're going to have a slope of 0 still, but now we're in the negative region of the graph. So this object is moving with a constant velocity of whatever value this happens to be. Let's call it -5. I don't know. Okay, and so this is moving with a velocity of -5 meters per second, for example, the whole time. So it's moving the whole time at this same velocity. My slope is 0, meaning my velocity is not changing, which is what it means if you have constant velocity. It's in the negative region. That's how I know I am moving backward. So again, you have to interpret it correctly, because if you just glanced at this graph and you weren't paying attention and you read it like it was a position time graph, you would tell me, oh, that object's at rest behind the reference point. And that's not what this says, because this is a VT graph and not an XT graph. So make sure you check the y-axis. Anytime. Okay, so you can go from one type of graph to the other. We've talked about both now. This XT graph here shows something moving backward at constant speed, and I know that because I have a negative slope and a straight line. This VT graph also shows something moving backward at constant speed. Okay, so that's two different ways to represent the same motion. Okay, specifically if I want to put numbers to it, the slope of this line would be equal to this velocity. So if my slope here was -3, then this line had better be plotted at -3. Okay, they would both represent the velocity. And the reason that works is, guys, slope is rise over run. On an xt graph, rise over run would be change in x, change in position, over time, which is the equation for velocity, change in position over time. So the slope of your xt graph will give you your velocity, and you can then make a vt graph from that. Anytime you divide your y-axis by your x-axis, find slope. And that's not just for this graph, any graph. If I give you a graph and you have a list of equations and you're like, oh, this divided by this, that's on my formula chart. Okay, cool. That means the slope of that line is equal to whatever that value is, because slope is rise over run. Okay, so you can go from a graph and take a slope and it has a meaning, and if you're not sure what that meaning is, you can see it on the formula chart, what that number would represent. For this specific one, it's velocity. You can also go from a VT graph and use information here to tell you about your XT graph by finding the area. Okay, I think I talked about this on the first week when we looked at some different graphs. We talked about area under the curve on your graph. The area here would represent the displacement of an object, because the area, length times width, would be the velocity times the time. And if I rearrange this equation, velocity is displacement over time, velocity times time is displacement. So this shaded kind of orangey area would represent the displacement of the object at whatever time this would be if I had some numbers here. Okay, you could find that area and you would know how far you had traveled. It would tell you your displacement. Anytime you multiply your x-axis times your y-axis, find area. So again, same thing. If you're looking at a graph and you're like, what can I do with this? And you have an equation that says v times t equals delta x, then you know that the area of that graph will tell you your displacement. Okay, or the area of a forced time graph. That'll tell you something later on when we get there. You guys got a forced time graph the other day in your lab. I didn't have you use that area for anything, but it had a meaning. And we'll talk about it more next semester. All right. But anytime you multiply your x-axis times your y-axis, find your area. Okay, so that's where our notes are going to stop today. And so I'm going to pause and I'm going to start talking about the lab that we're about to do. You guys should have picked up a copy of the Toy Car Lab. The Toy Car Lab says, directions, make a list below of questions you have come up with based on playing around with the cars. So obviously I'm going to be handing you a couple of cars in a second. And then you're going to circle the questions that are testable. If you have none, make sure to include questions presented in the class discussion. But you need to highlight the question you decide that you're choosing and that you end up designing an experiment for. Okay, so we're going to kind of do an investigation that's a little bit open-ended. You're going to look at it and say, okay, what are some different things I could test? And it has to be testable in this room with the materials that we have. So if you're like, I'm going to use a radar gun. No, you're not. We don't have any. Okay, so don't put that. But you're going to design an experiment today. So I need you, and we're already in groups. If you're okay, working with the people you're sitting next to, then you're already in a group of 3 or 4. But if you want to move around or reorganize, you can. I'm going to, in just a moment, give you one toy car and one toy truck. I don't have all trucks, but basically you're going to get 2 different things. Let me show you what they look like. All right, you are going to get, in just a moment, one pullback car. So this one is kind of a truck, it's a Bronco. And one battery-operated constant velocity cart that looks like this. Okay, so there are 2 different things. This one operates the same way that your toys did when you were a kid. You just pull it back and let it go. Okay, this one is battery powered. Please do not pull it back or push it forward. There's a switch. It turns on. It has lights. I don't know why, but it does. So this one, you're not going to pull back or anything. This one does. So you'll get these in a moment to play around with so that you can start thinking about different questions that you could test. Okay, but before you do that, let me go ahead and mention this. Okay, here are some different materials that I'm going to provide you with so that you can use whenever you're coming up with your idea. So if you're trying to think of like what you could do, you'll have access to meter sticks, you'll have access to stopwatch. I'm going to let you use your phone for that. Tape, a motion detector, which I put it back, but that is kind of like a radar gun, to be honest. Ticker tape, which is, remember how we did the dot diagrams and they show dots? Well, ticker tape, you attach it to something that's moving and it just pulls the tape and then it just makes dots as it pulls it. Okay, slow motion video if you want to use your phone for that, and then of course the toy car and toy truck. Okay, so keep that in mind as you're thinking about different questions that you could test, and they have to be testable in this room, and I'm going to ask you guys to share in just a moment. So I'm going to come around, pass out some materials, let you guys have a discussion at your table, and think of things that you might be able to test with these materials, and then we'll kind of share some ideas, whole group, and come up with things that we could actually test that would be good tests to do in this room.